Good morning, ladies and gentlemen. Welcome back to your favorite class. Rawr! Announcements. Your fracture homework is due next Friday. That's it. I've been soliciting student-submitted memes. So here's a student-submitted meme. But there's an error. Ah! Anybody find what this error is? I'll give you
squared, feet per second squared.
Yeah, it should be feet per second squared. Ah, these sophomores. Dang it. What are they doing? All right. Well, anyway, I appreciated the spirit of the meme. And if you want to make a meme for meme of the day, go ahead. Maybe you'll see it appear, and maybe I'll make fun of it because you forgot your square. All right, anyway. Back to reality. Oops, there goes gravity. Maybe I've had too much coffee already. Maybe, just maybe. Okay, so we're going to pick up our discussion on fraction mechanics. And like I said before, fraction mechanics, the most common way that composites fail. So definitely the most interesting mathematically and the most useful practically. So let's get back to business. Or as they say in Milan, let's get down to business. All right, so continuing. When we left off, we were talking about the energy method for doing fraction mechanics analysis, and that is by far the dominant mode of analysis for composite materials. So we talked about the different modes of fracture, and we talked about the maths associated with a single fracture event. So just a reminder, if we have a solid brittle material, let's say like an epoxy, so we haven't really even gotten to composites yet, and that material is just kind of like this rectangular prism here. It's got width into the page of B. And it's got some original crack length, which we call A0. And we're going to load this up. And we'll say that we're loading this with some load P. All right. So your typical load displacement for a linear elastic material, is going to look like this, where you have displacement on the x-axis and you have load on the y-axis. This guy is going to load. And then at some point, it had all it stands, it can't stands no more. All right, load. And then the crack will propagate inside of the material to relieve the energy that you have put into the material through this external force. All right, so it relieves that energy by fracturing and relieving that load. Okay, so we have this fracture event, and that fracture event is going to cause this crack to propagate from where it is to some further distance down the line. And we typically denote this additional length as delta A. Right? So right before the crack, we have this value here, which is something like delta F comma P1. And after the crack, we still have that same displacement, assuming we're in displacement control on our load frame. And here we're going to have the same displacement, delta final, and this will be P2. All right. Then if we unload this sample immediately after this fracture has occurred, because we're purely elastic and there's no plasticity in the sample, it unloads right back to where it originally started here at the beginning. So this is kind of our load displacement. And in this particular instance, here's where our crack propagation delta A has occurred. All right, so it occurs when we lose that load. So we broke down this load displacement and said that the work that went into this is the integral under the entire curve, so from 0 to delta final of P delta d delta. So the total work in this guy would be this area contained by this whole kind of triangle here. And pretty obvious to see that that total work is 1/2 the base of this, which is delta final, times the height of this, which is P1, right? So this is the external work that we put in. Right. And because our energy balance was something like the total work that went in must be balanced with the elastic energy plus the energy of fracture. That we could break this down into two distinct events. And we know that the amount that we recover is whatever energy is relieved to us or given back to us after our unload. And so after we unload, which here is our unloading, we have recovered the energy that's underneath this portion of the curve. So here, this is your UE, where we can show that this UE is simply 1/2 this delta F, again, because it's a triangle, multiplied by P2. Right. That allows us to solve for the energy of fracture, which is the energy lost during this fracture event. And obviously that is the balance of the energy between the total work and the work that we recovered from the elastic portion of the event, which here would be kind of like this area on the curve. Here is your value of D, where D is the energy lost to fracture. And if we do something like D is equal to the total work minus the elastic energy, then you end up with an expression for D, because of the elastic nature of this particular guy, of something like 1/2 delta final times P1 minus P2. I think I may have had these backwards in the lecture notes on Wednesday, so make sure that you have this general definition, okay? That the energy of this fracture event is 1/2 delta F P1 minus P2. All right. Now, given that idea, it took this amount of energy, and remember the energy here is going to be in something like joules, or you can pretty obviously see that this is like newtons per meter, right? Just from the units in this particular problem, newtons times meters is joules. All right. So this is the energy loss to fracture. And when we have this energy that's lost to fracture, we created a free surface. All right. So we took that amount of energy to create for us this new surface. So the new surface that's created has a certain area. And the crack that we opened for that particular crack is delta A, and width into page is this variable B. So the area that we opened is just delta A times B. All right. These two definitions of the amount of energy lost to fracture and the area that we open lead us to define what is known as the critical strain energy release rate. And that is GC, or you may see it as G1C, G2C, or G3C, depending on the mode of fracture that we have, is equal to the amount of energy that it was required to open the crack, which is D, divided by the area that was created when you did this fracture. All right, so here we know that D is 1/2 delta F P1 minus P2, and the area that was opened is B times delta A. So in short, the energy required to open a crack, one little crack that is propagated, is going to be equal to delta F P1 minus P2 on 2 B times delta A. Okay, so there you go. If you want to determine the critical strain energy release rate for any particular solid that you know to be brittle. All right, so think epoxies that we work with, and even we can kind of consider composites generally brittle in the future, but any brittle material. If you have any brittle plastic, or even there are some like a glass. All right, so glass is a good example. Put a little pre-crack in there, measure how long the pre-crack is. Load that thing up in a load frame until that crack propagates, and then measure the amount of load that was reduced during that propagation and measure how long the crack went. There you go. You got your answer, right? So this is one way that we can calculate the critical strain energy release rate for any particular sample. Now, if you're doing an experiment, usually you don't want to just go with like one value. Okay, so you don't want to just like run one test. Usually it would be more useful to have like multiple tests. Okay, so what people do in real life, if they know they have a brittle material, is they'll load it, load it, load it, and then they'll see a reduction in load and constantly track the crack at the same time. So you load, 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 you see the crack jump, okay, you know what crack jump was associated with what reduction in load. Then you keep loading, then you have another reduction in load, another crack propagation, another reduction in load, another crack propagation, so on and so forth. So you can build like multiple crack openings and energies for each associated failure inside of your experiment. Okay, so you go, go, go until you've run out of like material and it's fractures all the way through. All right, so practically speaking, it would be more useful if we had some experiment where it was like load a little bit, then fail, load a little bit, then fail, load a little bit, then fail, so on and so forth. Okay, so that is a specific type of brittle fracture known as stick slip fracture, which is what we're going to talk about now. So, multiple discrete events. All right. So if you want to run an experiment and get multiple data points, this might be something that you're hoping for, right? So with multiple discrete failure events, get multiple values of GC. So if you think about a load displacement curve now, for this type of behavior, here's your displacement, here's your load. You're going to have something that looks like this. We load up, load up, load up, load up. All right, so here's our loading. Then we hit a point where we can't stand no more and we fracture. So bang, we lose some energy to fracture. Now I could unload at this point and determine what was the energy associated with that individual event. Okay, so if you wanted to unload, you could unload and determine what the energy was, for instance, of the fracture, which we know is contained in this area. And then the elastic energy that was recovered is contained in this area, and away you go. All right. But instead of just doing this one event, what we typically want to do is have multiple events. So here's like event number 1. But we could also continue our loading. And what you want to note here is that now like the compliance of the sample, basically like the elastic modulus of the sample, will always sort of like point back to 0 for this particular sample, because if we unload, we're going to unload with the elastic modulus that would sort of like put us back to a 0-0 condition. So we will continue loading now with the slope that we would have that would reach us back to a condition of no displacement and no load. That's sort of a requirement of a purely elastic material, is that when you unload it, there's no residual displacement. All right, so here's like event 1. All right, so in this particular situation, you've got delta A, let's call it 1, and here's like P1, and let's call this P2. All right, so we load some more, load some more, load some more, and then we have another event. All right, bang, fractures again. All right, so maybe you call this like P3 and call this like P4 or something. All right, you can kind of call it whatever you want. And here's our next event, delta A2. All right, so Continue loading, continue loading. I'm sort of run out of space here. Trying to fit a lot in here. All right, continue loading, continue loading, continue loading. Another fracture event. Continue loading, another fracture event, and then finally, all right, we're done. We've seen enough. All right, this is the general idea. We can define a general location of the load and the displacement so that we can talk more generally about the ith fracture event. So let's do that. Let's say here that generally this displacement and load condition is displacement delta I. And here this is going to be pi minus. All right. Why do I say pi minus? Well, that's because that's the load on the sample right before fracture. So pi minus. That's like if you ever did limits in calculus, like a 0 minus or 0 plus. So like approaching the limit from the left or approaching the limit from the right. Here we're approaching the fracture event with the load that's coming at it from the left. So right before it fractures. All right. So we have a similar point down here that matches, which is like delta F comma pi plus, not delta F, delta I. All right. And since we're in displacement control, this displacement value doesn't change. It's delta I for both points. We're assuming that it has the same crosshead displacement on the sample as we're loading it. We're just changing the load because of the fracture event that's occurred. All right. Right before this, we also have a crack length, which is AI minus. And here we have a crack length of AI plus. So let's define some of these things. So for the ith fracture event, the crosshead displacement is delta I. The load right before fracture is pi minus. All right. The load right after fracture is pi plus. And then we have the crack length before fracture. Here is going to be the total crack length, AI minus, and then the crack length after fracture is AI plus. All right. And when I refer to crack length here, if I'm looking at a sample, and it's fractured up to here, and then the additional fracture that we incur is this length, then AI minus is this original length. God, it's kind of hard to show this. The total crack length, AI minus, for the ith event. And then right after the crack is propagated, we have this length here, which is AI plus. All right, so I'm talking the total crack length here, not the crack advance, which is different. Delta A is different than A. Delta A for the ith event is A plus minus AI minus. All right, kind of a little complicated, but let's spell that out exactly. All right, in this case, the crack propagates. A length of delta AI, so that is the crack advance for the ith fracture, is equal to this AI plus minus AI minus. So whatever the crack length was after the fracture minus whatever the crack length was before the fracture, right? All right, then in this case, so for the ith fracture, energy is the following. The fracture energy associated with the ith fracture, so this is di, the energy of fracture I, is 1/2 times delta I times whatever the load is right before. So this is pi minus whatever the load is right after, pi plus. Right. That means the critical strain energy release rate for ith event is this GCI is going to be the DI over delta AI times B I over delta AI times B. Remember, B is the width of the sample into the page. And so this here will be delta I PI plus, sorry, PI minus PI plus, all divided by 2 times delta AI times B. And there is your critical strain energy release rate for the ith event. So if you run an experiment with multiple of these events, you can just program your MATLAB loop to calculate the critical strain energy release rate of each particular event if you know all these values. If you know what is the displacement at each fracture event I, and you know what is the amount of load that's lost in each one of the events, and you happen to know the crack advance during each one of those locations. So if you're setting up a fracture experiment, you need to know the displacement, you need to know the load, and you need to somehow track the crack during the experiment. All right, that's the hardest part if you're ever doing a fracture experiment, is that you need to know how much crack advance there is, because you need to know your crack opening area so that you can normalize by this area appropriately. All right, this type of fracture in the biz is known as stick-slip fracture. I think the name here sort of speaks for itself, right? So it sticks until some point where it's released, and then it slips, and then it's stuck, and then it slips, and then it's stuck, and then it slips. All right. Stick-slip fracture is very, very common for composite materials. I'll make this caveat here. It's very common for woven composite materials. All right. And just to remind yourself what a woven composite material is, I think I want to bring in a picture here, but I don't know where that picture is. Yeah, I'm not going to be able to do it right now, but let's try to draw it the best we can. All right. So remember, the fabrics of composite have this, like, think about a plane weave. So when I say like woven composite materials, think like plain weave, satin weave, twill weave, etc. Okay, so what you should have in your mind is like a composite with layers that look like this. If you're looking at them from the side, here's like one layer of the composite, and you're gonna have like this woven structure. So you have kind of like layers that look like this, and then into and out of the page here are the toes. All right, so that's like one woven layer. All right, so this is like toes across the page and toes into the page. Here's a, and when you stack these up against each other, what happens is, let's say we have kind of a repeating pattern here. So I'll try to mimic this as best I can on this next lower layer. And what happens is if I'm trying to propagate a crack through this like woven system, what happens is the crack's going to propagate until it hits like this rounded edge of the fabric. So hopefully like we see this rounded edge and it sort of gets pinned there. Okay, so the crack will propagate, it hits this rounded edge and it sort of like stops. And then it loads, and then finally I can like overcome this like hump that is like this woven layer. In actuality, it looks maybe more something like this. Okay, so it sort of gets like pinned by that particular toe that's coming into and out of the page. And then so it builds up here, and then it shoots through to the next guy. All right, so that's what I mean when I say that woven composite materials very commonly exhibit this stick slip behavior. You load it, the pin between the fabric layers then releases, right? Because it's kind of like pinned to this in plane toe. Releases, and then it goes to the next one. Pull, releases, goes to the next one. Pull, releases, goes to the next one. All right, so I have actually a woven fabric here that I can kind of maybe show what I mean. And I polished this so I could like try to show it a little bit. I don't know if it's going to come through on the screen or not. Maybe it will, maybe it won't. I guess we'll find out in just a second. Let's see if my camera is good enough. I don't know. Maybe, maybe not. Probably not. It's still focused on my head, my stupid prison head. But I'm trying to show kind of like the individual layers of the fabric kind of woven over and under each other. And so you see how it's kind of, this is a woven fabric, a 2D woven fabric. And you see how like those toes are there? They kind of look darkened. And then there are lighter toes that are moving over and underneath them. What happens with this woven fabric is the crack tends to get pinned in between some of those like woven layers. And that pinning creates this like stick slip behavior. So a lot of times woven composites have analysis methods that look like this. All right, did that even come through? Like, could anybody even see what was happening there? I don't know. Gawking rabble. I have no idea. All right. So that's stick slip fracture behavior. The alternative to that is stable crack propagation. So let me share my screen again. All right. Let's continue with this stick slip quickly. So here we have this stick slip behavior where it like loads up a little bit, fracture, load up a little bit, fracture, load up a little bit, fracture, and you can create these discrete fracture values and discrete fracture events. So you know the energy associated with the ith fracture. All right, this allows you to create what is known as the R curve. All right, so let's explain what this is. All right, and this is for, in this case, the stick slip behavior. All right, for stick slip behavior, we have multiple values of GCI corresponding to crack length in the sample of delta AI, or let's just say the crack length is AI. So what I mean by that is you have this load displacement. displacement, here is load. We have all these individual events. All right, loading up, bang, 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 etc. So you have all of these individual events, and each one of these has associated areas of fracture. Right? So we kind of know this at this point. So each one of these like zones here has its own energy associated with fracture. Right. So here is like the energy associated with fracture event I, which we say is DI. And this guy has, at this particular moment, this is delta I, comma, PI minus. Here is delta I, comma, PI plus. And it has associated AI minus and AI plus. Okay. This results in, for us, after calculation, a vector that contains GCI and AI. So these are vectors. So you'll have like some value of GC, some value of GC, some value of GC, so on and so forth for each one of the events. All right, so think about like how you might look at this in MATLAB. All right. We can take these two individual vectors and plot them against each other to create what's called the resistance curve. And this is an important concept in this energy method for fracture mechanics. Now, what that might look like is instead of now just plotting load and displacement, we're going to plot crack length on the x-axis, and we're going to plot the associated fracture energy required for that particular crack propagation on the y-axis. So this is your R curve. And it's going to look something like this. Here we have on the x-axis crack length. Okay, so this might be like AI. And here we have the critical strain energy release rate, which we just call GC. All right. So here, let's say, is A0. And then there's like individual values that we know along the way corresponding to the cracked length of fracture event I. So each one of these marks is like AI. Right? So for the ith fracture event, we have the corresponding value of GC. So you're going to end up with discrete data points on here that look something like, I don't know, maybe the energy of that fracture event was there, maybe the energy of that fracture event's there, and here, and so on, and so on, and so on, and so on. Right? So these are all the data that you get from your one singular sample showing the GC value associated with each fracture event. This plot is known as the R curve. All right, so it's plotting all of your individual data points against the crack length corresponding to that particular fracture event. So this particular point here, if you want to think about it, is like your AI minus value, comma, GCI. So this is the crack length right before failure plotted against the fracture of the critical strain energy release rate of the ith event. All right, so that's the general idea. If you have a perfectly elastic sample, this line should be flat. So what I mean by that is these data points should all approximately fall on the same line, which I've kind of sort of like tried to draw there. All right. So If so, then the average of all GCI values is the reported critical strain energy release rate. So GC for the sample is the average of GCI. So on this chart, it is if we average all these guys and come up with this particular blue line as the average, there's your average GC, or what you would report from the test as the actual value of the critical strain energy release rate, GC. All right. This R curve, important. Anytime you manufacture a composite and you do a fracture test on it, this is going to give you a lot of information. And generally, if it's completely brittle, or if it's like a pure solid material, we're not talking about composites now, let's just say it's a pure epoxy material, and you do this test, or a glass material, it should be more or less very flat. And so regardless of the length of the crack in the piece, the associated energy required to propagate that crack any additional amount should be this critical value GC. So this allows you then to predict, okay, I have this material property now that I know for this particular piece, and that is this critical value. And so this here is a material property, much like elastic modulus is a material property. It should be consistent for the loading situation, regardless of the size of the piece, how you're kind of loading it up, what the crack length is, so on and so forth. So we're normalizing all the additional information here for things like what is crack length, what is load, all that. And built into this value of GC is this constant that tells you this material property, how it will behave in this certain situation. I think that's kind of cool. Fracture really is this crazy complicated thing, and to be able to just like boil it down to this one value for brittle materials, I think is really quite elegant and nice and unique. All right. So that is like your stick slip behavior. And for the stick slip behavior, you get these individual discrete events because you can sort of measure like the individual discrete events that occur. You load up, bang, load up, bang. Okay, you have these individual events that you can sort of measure. But what happens if you don't have stick slip behavior? What happens if you have a stable propagation? Now, what about stable crack propagation? All right, so let's look at that. So if you have stable crack propagation, what's going to happen is you're going to load up your sample, load up your sample, load up your sample. And instead of having these discrete failure events, bang, 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 where the crack jumps like a noticeably large amount, what's going to happen is you're going to load this up, and the crack is only going to move like a little bitty bit at a time, just a teensy weensy little bit, and almost small enough where you can't even like tell that the crack is moving, okay? Because the loading rate is like slow relative to the crack advance, you like load this up a little bit and you can see that the crack is maybe moving just like a little itty bitty bit at a time, but it's not a very noticeable behavior like this previous stick slip event. So what that might look like, crack propagates, I'll say slowly relative to crosshead speed. So now what's happening is you've got this sample. Loading it up. Some load P, and it's displacing some value delta. Here's your crack inside of your piece. And this crack is advancing very slowly with the load. So slowly that my pen doesn't think that my hand is moving, right? So it's just advancing ever so slightly, ever so slightly. So in that situation, you don't have stick slip behavior, you have stable propagation. Right? So the load displacement curve is going to look like this. Here's your displacement, here's your load. What's going to happen is you're going to load elastically, okay, until you reach a point where the crack wants to propagate. So here we load elastically, loading up, and then we get to this point where now the crack wants to propagate. But instead of like these big jumps like we saw before, it's just going to drop a little itty bitty bit amount. And so the load is going to drop very slowly. So what you'll see is something that looks like this. What looks like a lot of little individual events, right, as this crack kind of like propagates. That's the general idea. And it does kind of like flatten out with this general behavior. This is to the power of 2/3, but that's not important. The idea here is that this is not a straight line. This is a sort of a power law to the 2/3. All right. Okay, so we've got all these crack propagations that are occurring. And it's unreasonable for us to measure the crack propagation of each individual event. So we cannot practically measure each, I'll say delta AI and PI values. All right, so we got the sample, we load, and it's got this really minor crack propagation as we go along until we get to the end, and then we unload, and we know when we unload, it's going to unload back to its original position. So sorry about the drunken line. My hand is jittery, too much coffee. All right. So how do we deal with this? All right. Well, we can deal with it by knowing that there is a certain reduction in load associated with a certain known crack propagation length. So what I mean by that is that there are locations on here that we know. So let's say right here, this is some value of the crack propagation delta I and PI. All right. So here this is delta I and PI. And we know that from this like load displacement curve. All right, later on down the line here, we have another value, which is like delta J and PJ, right? So let's say I have these 2 points on this load displacement curve, and I happen to know what the crack length is at each one of those individual locations. So let's say I know at PI, delta I, comma, PI, that crack length is AI. I also know at delta J and PJ that the crack length is AJ. Well, with that, I have a change in displacement, a change in load, and a change in my created free surface through delta A. So that means if I were to like unload at any one of these individual points, I know that I would unload back to my home point, my home position, right? So that means that I know the elastic energy associated with each one of those individual points. I know if I were to unload from, let's say, delta IPI, that my elastic energy would be something like this, right? I know if I were to unload from delta JPJ, that my elastic energy would be something like this, okay? So the differences in those elastic energy between those two particular locations is the energy that you lost to fracture, right? So let's make that perfectly clear here. So the energy delta I comma pi is known, and that is the elastic energy at location I is 1/2 pi delta I. Also, at J, the elastic energy at J is 1/2 pj delta J. So the energy lost to fracture between those two events must be the difference between the two. Which is, if you sort of work the math here, and I'll simplify as I go, you could rearrange this for yourself, but just know that this is going to be true. Pi delta J minus Pj delta I. And this is the fracture energy between any two locations on your load displacement curve if you have this stable propagation behavior. All right. So now then, we know the energy that was lost to fracture between any one of those 2 points. And so if this is the particular situation, we know the energy lost to fracture between these 2 points is like the energy contained in this area here. Right? So this is our approximation to the energy lost to fracture between location I and J. Then the critical strain energy release rate between those 2 points is that value normalized by the area that we created. So then critical strain energy release rate between I and J is what I would say GCI. Okay, between like I and J, we'll just have some other notation here, is going to be this 1/2 pi delta J minus Pj delta I divided by the area that you opened, which is going to be delta AI times B, where remember delta AI is A J minus AI. All right, this is the difference in the crack opening between location I and location J. All right, we can rearrange this guy for a more elegant look, and this is what is usually presented in like textbooks, and that is 1 on 2b times delta A, 2b or not 2b, delta A, multiplied by pi delta J minus Pj delta I. This is what you'll normally see in any fracture mechanics textbook for brittle materials that undergo stable behavior. All right. So get your load displacement data from your load frame and understand that you're going to need to somehow identify when the crack is at like 5 millimeters, 10 millimeters, 15 millimeters, 20 millimeters. So if you can identify, all right, my load and displacement when the crack is propagated 5 millimeters is this. My load and displacement when that crack is propagated 10 millimeters is this. My load displacement when the crack is propagated 15 millimeters is this. If you can identify all of those values, then you can calculate multiple values of this critical strain energy release rate for this particular sample between each one of these individual IJ pairs, and you can construct again this R curve using those individual values. All right, so more on this to come starting on Monday. We'll actually show you for composites how this test is done. I'll show you some samples. I'll show you some data. We'll do an example problem, all the good things. All right, thank you for coming. I hope you have a great weekend. Try to get outside. It's supposed to be kind of nice this weekend, so try to get outside if you can. Get out of your house, quarantine, rawr. Okay, thanks.